Okay, hi everyone. This is Dan Barry, and welcome to this MAP webinar. Today's webinar is the first in a two-part webinar series we're hosting on the topic of fire modeling and prediction. We're going to come back next Tuesday with the second part of this webinar series. We've become much more interested in fire modeling and prediction, especially over the last year where there were fires around the world that had significant impacts. In 2017, there were massive, unprecedented wildfires throughout California. Some of the California fires from last year rank as the largest and most destructive in history. Nevada and Montana also saw some of their worst fire seasons in decades. And then there was really a story of wildfire around the world last year. There were massive fires in British Columbia, Canada, Italy, Romania, Siberia, and Russia, Brazil, South Africa, New Zealand, and Chile. And in Portugal, over 60 people died because of wildfires in June. So over these two webinars, we're going to explore efforts around the world to treat fires with more detail and sophistication in global and regional models and to predict fires on various timescales. We're really lucky today to have Francesca Di Giuseppe from ECMWF, Etienne Turini from Barcelona Supercomputing Center, Karen Mazuma from NASA GISS, and Sam Rabin from the Karlsruhe Institute of Technology. So three European colleagues calling in from the late afternoon, and really appreciate them taking the time to do it. And then Karen in local ET, so thank you for calling in this morning, Karen. And I also want to thank Emily Reed for pulling together the logistics and the speakers for this. It was a lot of work. We had to do multiple doodle polls to make this happen, but thanks to her for doing that, and thanks to the speakers for putting up with all of our emails as well. It's great to have this great group of speakers on this webinar, and we're really looking forward to it. So we're going to start with Francesca. Francesca, are you on the line?
Hello, hi. Thanks for the invitation.
Yeah, absolutely. So Francesca, I'm going to pass control over to your computer. And if you can click the Quick Start tab and the Share Screen button, we'll be able to see your slides.
So you can't see the share. I can't see the sharing button now. Sorry.
Yes, are you in the WebEx application?
Yes.
Okay, so if you click the Quick Start tab in the window. Alternatively, there might be a Share menu item on the top of your screen.
Quick Start, yes.
Okay, there you go. Great.
Here you are.
Yeah, looks good.
Thank you.
Whenever you're ready, please go ahead.
So, this is the title of my talk, Fire and Weather, and I have put a little picture of myself so you can see who is actually talking. In this talk, I'm going to touch some aspects related to our current capability of predicting fire danger from weather forecast. And I'd like to look at several time scales as well, and not just short or medium range forecasts. I would also like, given the time constraint, to use this time to talk about some opportunities that can arise also from looking on the opposite, that is taking into account fire burning process in numerical weather prediction, if this can actually improve also our forecast. Before starting, I would like to acknowledge the contribution of many colleagues here at ECMWF and somewhere else, which have really taken a lot of effort of what is going on at ECMWF in terms of forecasts in the last 5 years. So I wasn't sure if everybody knew what we are. ECMWF is an intergovernmental organization and has been producing weather forecasts in the last 40 years. We have several products. Maybe the most famous one is that we run a 15-day operation ensemble prediction system, which consists of 51 realization of weather forecasts, starting from slightly perturbed initial condition and different model physics configuration. We also have longer range forecast. So we have a bi-weekly extended range forecast up to 46 days and a seasonal outlook that every month is updated. From the perspective of weather application, we have been particularly active in the last few years. And this is mostly because there has been an European effort to actually translate the wealth of our weather forecast to run multi-hazard application. One important aspect of the European approach to fire management has been that since an early start, they really try to rely on weather forecasts to calculate fire danger. While traditionally forestry agencies usually use station data. And this was mostly because it was thought that for Europe, this would help coordination of resources among various partners and countries. In this picture, you see what is the outcome of this effort, and this is the European Forest Fire Information System, and it's a platform where we display weather forecast, fire forecast from our weather forecast. And you see a global map because the EFIS, the European platform, is actually being expanded into the Global Wildfire Information System. So ECNWF has been awarded the provision of fire forecast from 2017, and we have started this operationally. From our point of view, so how do we use our weather forecast to forecast fire danger? Essentially, there are different modeling approaches, but in general, the idea is to use the long-term and short-term drying of the available fuel to characterize how much of the fuel is actually available for burning. And wind is usually used to give an idea of inflammability condition. Usually, I mean, for easy, this is one of the possible models, the fire weather index. It is just based on weather information. So these two indices are usually combined to give an idea of what is fire danger. What is important here to notice is that this index is just designed to highlight weather conditions favorable to burning. They don't attempt to predict ignition itself. As ignition is very rare and a very rare event, very often you have a map of very high danger, but there is no really fire taking place. So just to give an idea what this fire weather index means, essentially, this is an index that gives an indication of the consequence of a fire, but only if one was to start. Therefore, the high fire danger, the more dangerous are the condition, and more uncontrollable might become the fire. This is just an example of a paper from the Canadian colleagues. They show how under different FWI conditions, you can have a very different kind of fire spread. So FWI is actually an index that should be used as a trigger to take action to prevent or control a possible fire. And it's an index that is almost exclusively dependent on weather. So we can ask ourselves where this index is actually a good indicator of fire index, giving the availability of weather data. And these maps show you a little bit of a global consideration of where FWI approach might be suitable. And here I call this sort of potential predictability because I use data to calculate FWI that come from a reanalysis. Therefore, these data are the best possible data and they don't have the error of the forecast. And here, essentially, we just try to identify where high fire danger corresponds in a statistical sense over many cases to real fire events. And real fire events are here, for real fire events, here I use just the GFED burn area data set for the period 2000-2015. The general finding of this study was that essentially where vegetation is abundant and then for fuel is not a problem, then most of the time weather is what controls really fire burning. But in area like savanna where bushfire takes place, then vegetation is scarce. Maybe the FWI might not be the best approach. It's not only weather controlling this predictability. So, as Ben already said, there has been quite a few cases of very bad fires during 2017. It was a very active season with many devastating fires. And I have two examples just to have a look if using weather forecasts can actually allow us to predict where these fires are going to occur. So in this first example, I'm looking at medium range forecast, so 10 days ahead. This is the Chile fire that started in January 2017. And there were a very long-lasting sequence of burning events that took place during this month, mostly concentrated in central Chile, as depicted here by the observed fire relative power. This is a map of what was the fire danger predicted 5 days ahead. And you can see that very high danger conditions were highlighted where the fire actually took place in a region, as I said, that is much larger than where the fire event took place, because this FWI doesn't really predict ignition, but just a probability of danger condition. The interesting thing, I think, is the diagram on the right, which shows the number of pixels in Chile that were above the high fire danger for every forecast issued in January 2017 and for 10 days horizon. So you can see that 10 days ahead, if you looked at the persistent forecast for 10 days ahead, you had quite a good indication that extreme danger, quite widespread, were forecasted for Chile in that period. And this can give a good indication for managing and control. Another example, which is quite interesting, is clearly the California fire that has already been mentioned. It was quite extreme, very destructive, and probably, in the next talk of Etienne, we'll discuss this in details. And again, the forecast, using the forecast, medium range forecast from ECMWF, this is for the 9th of October 2017, one of the many days in which fire were raging around California. And you can see that, the forecast is quite good in predicting extreme, between very high and extreme danger condition. But what is interesting, I think, in this example is that using an ensemble prediction system, like the one of ECMWF, it is possible to sort of attribute a confidence measure to the forecast. So in the lower part of this figure, you see that this is a sort of probabilistic product that you can create, and shows the number of ensemble members, so using different forecasts, which were above the high danger level shown above. Therefore, you have not only the indication that your forecast is going to be bad, but you also have an indication that you're very confident about that forecast. Another example I want to make is about using these forecast tools and looking at long-range forecast, for example, 26 days kind of prediction, so in the sub-seasonal to seasonal time scale. In this case, we think the use of this product will be help not much to establish a reaction measure for an event, but to actually assist the predecessor planning. And one of the best examples is probably the fires that occur in Indonesia. Since these are mostly human-caused, therefore, the ignition is almost 100% certain on a territory that is on peak, and therefore, often fire rage out of control when there are extensive droughts, for example, when it's driven by El Niño condition. And since we know from weather forecasts that El Enso is quite predictable, even at a monthly, seasonal or seasonal time scale, we can therefore expect that this predictability can be translated into fire forecast predictability. And this is just an example, for example, an uncalibrated, let's say the values for this FWI index mean for September 2015, that so is a very bad example of fire in Indonesia because it was a very strong El Nino. And the point, and this is the burning that went on in September 2013 that involved much part of Borneo, Sumatra. And if you look at the FWI, you can see that, of course, there is a signal, but this signal of FWI for, if you would compare these values with European values, wouldn't be that high. So the point that I want to make that when you look at this time range, what it makes sense to do is to look at FWI calibrate or anomalies compared to the climatological mean in a very, I mean, you can extract more information in a very similar fashion of what you would do. Also in weather forecast, you look at anomalies more than real values. And therefore, I mean, this is just a sort of tercile-based kind of calibration that we have done. We know that FWI is not the best indicator for Indonesian fire. Maybe the drought code would be better. But this is just an example of what you can actually achieve using weather forecast. So the second part of my talk, very briefly, I would also talk about some opportunities about on fire prediction. Because I mean, of course, we are interested in how we can predict fire danger given the weather condition, but there are also some possible feedback on the inclusion of fire emission might have to improve the weather forecast. There is in general a general consensus that by including more process in weather and climate situation simulation, we can bring high benefit as well to NWP. And a key component, this is just a study that has been published in climate change in Nature Education Knowledge, and show the transition from simpler climate model to global health system modeling. And a key part is actually occupied by the inclusion of aerosol that are emitted during the burning process. So just to highlight what aerosol from fire can do to weather, there are actually two effects. What is called very well-known direct effect, and it's due to the fact that aerosol, especially from fire, are mostly black carbon. Therefore, they tend to be more opaque and can therefore change the albedo and absorption property of the atmosphere. And by changing the radiative budget, of course, they can impact the dynamics of the atmosphere, and therefore the global circulation, as shown by this paper by Tompkins and Hall, where they saw that just changing the climatological database of the aerosol in ECMWF model, they could enhance or suppress the African easterly jet by almost 20%. There is also another effect that aerosol can induce on weather. This is due to the fact that aerosol act as cloud nuclei, and therefore they change the cloud formation process. This process is less, let's say, less understood, less known. So if we just concentrate on the first direct effect, at ECMWF there have been some simulation looking how, when you take into account this effect, how this can actually change the local weather. And we took as an example the big Indonesia fire that, of course, was very long-lasting and extreme, and therefore could have a signal, even leave a signal into the weather. So if you look at what happened again in Indonesia in 2015, this is just a map of all the active fire that went on between August and October. And they actually, if you look at what is the anomaly produced in aerosol, you can find that in the area there was an anomaly that was up to 2,000 times the climatology. So you can ask what happens if your model is able to see this anomaly. And some run has been performed by Benedetti and Vittard. And they found that actually if the model is aware of this anomaly in aerosol, it doesn't use just the climatology, then you can have a cooling effect that is of at least 2 degrees average over, for example, the season of October. So it's a very big, at least, thermodynamical signal. So you can, of course, expect as well that the inclusion of aerosol, when the model knows of these anomalies, they can actually reduce the bias in the model simulation. And this is just one last slide to show you that the inclusion of aerosol can actually be beneficial as well, can create a feedback in the weather forecast. So in the plot, and the plot on the top, you see what are the mean bias in temperature at week 4, so for a long-range forecast, when you take several year simulation between 2003 and 2015. So for every forecast in this time range started the 1st of May. And of course, there are areas of the planet with strong errors. When aerosol is not a climatological values anymore, but they are allowed to change by year to year, you can see that there is a strong, at least a reduction of the bias almost everywhere, because of course it's a component of the system that you are taking into account. So I think I'm on time, I hope so. Just to conclude, I would like to revise what few points that I think are interesting to take home. The first one was how accurate can be fire forecasts starting from weather forecasts that are uncertain themselves. And when we start this work and we talk to the Portuguese Met Service, they say that from their purpose, fire danger prediction should really be accurate at least 3 days ahead. And looking at the few events of 2017, I think that the weather forecast itself, accuracy, might be in reach to achieve this level of accuracy, especially if the information is complemented with the confidence level that we can give, because now we have ensemble prediction system, so we know, the possible error on our weather forecast. And also there is an opportunity of start to use this fire danger prediction at the longer lead times, for example, subseasonal to seasonal. And more information can be extracted by looking at an anomalies compared to, the climatological values on a certain area. And finally, since I'm a meteorologist, and then I always think back to NWP, there is also a great opportunity in trying to include evolving fire in weather forecast, because we can see that the knowledge of this event, large event, especially in our model, can actually highly increase the predictability. So these are my conclusions. Thank you very much for your attention. If there are any questions, I would be happy to answer.
Great. Thanks so much, Francesca. I thought that was a really wonderful introduction to a wide variety of topics that we're going to cover today and next week. So I really appreciate that. It was a very interesting presentation. I think in the interest of time, we actually have to move along to the next speaker. But if there's time at the end, maybe if you have a question for Francesca, you can send me a chat message in WebEx or take a mental note in the room. So thank you, Francesca.
Okay, thank you very much.
Okay, next up is Etienne. Etienne, are you there?
Yes, I'm here. Can you hear me?
Yes, yes.
All right.
So I just passed control over to your computer, and if you can go to the Quick Start tab and then click the Share Screen button, you'll be able to see your screen.
All right. So, so I'd like to thank you for the opportunity to present in these really interesting webinars. So my name is Etienne Tourini, and I'm working in the Barcelona Supercomputing Center, and we have a climate prediction group within this center. And today I'm going to present one part, on one side, the plans that I have to do seasonal prediction of fire risk, and I'm going to show in more detail a study we've just made on the wildfire events of California in 2017, trying to understand the difference between the influence of climate and weather in those extreme events. So the motivation for all of this work is that we know that wildfires are a great source of biomass burning and pollutants, as well as atmospheric CO2. Fires such as the Amazon basin and Indonesia, as Francesca showed, wildfires are affected by fluctuations in SST. On the other hand, in Europe, the countries that are more affected by wildfires are in the Mediterranean basin and occurring during periods of drought. And we know that 2017 was a very extreme year, particularly in Portugal and also in other Mediterranean-like climates in California. And so in light of these points, seasonal prediction of wildfire danger or wildfire risk is a priority for health, safety, and economic welfare. And as there are, on one hand, several short-term fire danger systems which in place, and particularly the EFFIS, which Francesca mentioned, there is no operational seasonal wildfire forecast system in Europe and only a few in other continents. And so the work that I'm working on is the SP Fire SD, Seasonal Prediction of Fire Danger using Statistical and Dynamical Models. It's a Marie-Curie fellowship. And I propose to develop and assess seasonal fire prediction capability through different focuses. So one using both statistical or dynamical models. What I'm presenting here is the number one here, which is the fire danger indices approach. So simple fire danger indexes computed from seasonal dynamical climate prediction systems, such as that given by ECWF. And I also have two other approaches. One is just statistical, and the other is a dynamical approach using the LPGS model, which is part of the EC Earth system model. And I'm not going to talk about that today. And basically, in the my first work package basically has three parts. And one of them, which I'm going to talk about here, is the validation of fire indices. How do observationally derived fire indices relate to fire danger? And in a more general sense, I would like to the study to make an extension of the EFFIS or the Global Wildfire Information System to seasonal timescales using predictions of fire weather index from multi-member operational seasonal prediction products. And we're going to start this work in June when I'll be visiting ECWF to improve, basically to kickstart the whole project. So basically, the Canadian Fire Weather Index is used operationally for forecasting of fire danger in Canada and also in Europe. And relies on observations of precipitation, temperature, wind, and relative humidity. I'm just presenting really quick. This is just an outlook that's done by the European Forest Fire Information Service of 1 to 10 day forecast of fire danger. And what the same system does for seasonal prediction currently is basically showing temperature and precipitation anomalies. So I think there's quite a lot of things that can be improved in the sense on seasonal timescales. Now I'm going to the second part of the talk about the wildfire season in California of 2017. It was the costliest on record, with $18 billion in damages and 43 casualties. So there were two periods that were intense. So first in October around the Napa Valley, the Tubbs fire was the most destructive in U.S. history. It was thought to be caused by warm temperatures and strong winds at the time. And later on in December, Southern California suffered from many wildfires, and particularly the Thomas Fire, which became the largest in California history. And again, it was thought to be fueled by severe Santa Ana winds and warmer than average temperatures. So for this work, what are the important relative importance of climate versus weather events? So climate, which being the drought, versus the weather events, which would be strong winds. So we use the Canadian Fire Weather Index to compute daily fire risk from observations, and we try to find out which of the conditions were responsible for these extreme conditions. So here I show you the study area. So the data source that we use for this are the burned area products from the MCD 64A1, the graded to a quarter-degree grid, and quite a few remote automated weather stations around the areas of interest. So here in October in Northern California and December in Southern California. And I used ERA interim reanalysis as well as North American regional analysis to be able to analyze a longer time frame. So you can see here data from Cal Fire, so quite a lot of burns, quite a lot of fires happened during the year 2017, where we see the Thomas Fire clearly stands out. And the question, well, was 2017 extreme? So first, if you look at burn fraction from the MCD64A product, you can see here on the left more or less climatology of the 17-year period. And here is the burn fraction on the right of 2017. So clearly much more activity than on average. And actually in some areas, these are basically the only events that happen in the area, which kind of gives you a climatological background. What was done to evaluate how extreme the year 2017 was? Here on the left, I show you the computed fire weather index. So this is monthly mean for December. I'm only concentrating on December. And so the monthly mean value of the fire weather index at one of the stations in the fire was much higher than the climatological average, which is 20. And here on the bottom, I'm showing a measure of how extreme it was in the sense of how many days in December were above the 90th percentile of all of the Decembers. And in this case, you have 80% of days of December 2017, which were very extreme. So we see that the fire weather conditions were really conducive to these events. And here on the right, I'm showing the temperatures, the maximum temperature, which goes into the calculation. And again, the values were for the weather stations and the reanalysis were highly above average. And in terms of extremes, well, 40% of the days were above the 90th percentile. Which means that, yes, it was an extreme in the case of temperature. And we detected a linear trend in the North American reanalysis data of about 0.05 degrees per year, which, if you extrapolate that to a century, would be about 5 degrees per century of maximum temperature. So perhaps global warming could have contributed maybe to, in the time of the study, to 1 degree warming. Now, that is not as much as the anomaly, which is 5 degrees. So climate change could have contributed, but well, I would not say that it was the only factor. Trying to figure out if wind was an important factor, then here I'm plotting the wind speed. And actually turns out that on average, the wind speed was lower than other years. And here on the bottom, we have the number of extreme days, which was also lower than on average. Therefore, we conclude that wind was not an important factor. Perhaps it was winds themselves, of course, did spread the fires, but 2017 was not an extremely a year that wind conditions were conducive for stronger than average wildfire events. And in terms of precipitation, well, we also see that precipitation was a leading factor because There was a monthly mean anomaly of about 2 millimeters per day. And in terms of extremes, this is the number of days below the 10th percentile, so kind of different. So again, higher than on average. So both temperature and precipitation created drought conditions in December. Looking at maybe a more spatial, in a more spatial context, here we have the burn fraction, the climatological burn fraction, and on the bottom it's anomaly, so very, very high anomalies of burn fraction. And the fire weather index was very broadly anomalous over most of California during the month of December. When we look at wind speed anomalies, they were not so extreme, and actually in the area where we had the fire on the west of this area, there were actually some negative anomalies. So again, we don't see that wind was a contributing factor. However, if we look at temperature anomalies here, they were quite widespread in the whole area, as well as relative humidity and precipitation anomalies. So these are, we can see that these are play a key role in creating the strong weather conditions. And now looking at more a little bit longer time slices where we can see the fire weather, temperature and precipitation anomalies in the months leading to the event. So fire weather index was broadly positive. The anomalies were broadly positive. These are again monthly means, which were caused by both extreme anomalies in temperature of some places 4 or 5 degrees in those 3-month periods. The only place where you can see that fire weather index was negative, the anomaly was negative, is actually during the month of November, where you had some extra rain here up in the north, which probably helped create a lower value of the fire weather index during December, because the fire weather index has some kind of memory. So this perhaps would explain why the fires were much more intense in December and not in October. So conclusions about this work: although the Santa Ana winds were important for fire spread, they were not stronger nor more frequent than other years. We identified that anomalously warm and dry conditions, which persisted for months, were key factors in creating these extreme fire conditions. We detected a long-term trend in temperature, but we need more work to find out what's the relative contribution of climate change. And future work, I'm going to finish my talk with this. What will we be doing in the future? Will we repeat the same analysis for the 2017 summer fires in Portugal, which, as we all know, had created many casualties, and also the fall fires in Galicia, Spain, which were quite unusual. And then we will work on seasonal prediction of fire risks using the same kind of approach, but with operational seasonal prediction products such as the ECMWS System 5, predicting the frequency of days in which extreme fire weather index are forecast a few months ahead. This hopefully would make authorities aware of extreme conditions and to be able to be prepared ahead of time. And if you combine this with a reliable short-term forecast, such as that presented by Francesca, I believe that this could prevent loss of property and life, so that the agencies know a few months ahead of time that they should be careful. And of course, the actual actions will be taken a few days before the events happen. And the work will be focused on the 2017 wildfires in California and Portugal and Spain. So with that, I'd like to thank you very much, and if there are any questions, I'll be happy to answer.
Great, thanks, Etienne. That was a really nice discussion of the factors that led to the California fires, so thank you for that, and it's great to hear all the work going on at BSC. I know you guys have an interesting suite of applied prediction products growing there. It's been kind of fun to watch those develop. So we have time for a quick question, if there is one. If there's a question on the WebEx, you can send me a chat message, let me know that you have a question, or you can raise your hand in WebEx. If there's a question in the room, we have a moment. Anybody have a question for Etienne? Okay, well, Etienne, if anything else comes in, we can come back to you and let folks ask a question, but thank you for that. That was great.
Perfect, thank you.
Okay, next up is Karen. Karen, are you on the line?
Yes, can you hear me?
Yeah, we can hear you. I just passed control over to your computer. So, perfect.
Can you see my presentation?
Yeah, looks good. Whenever you're ready, go ahead.
Okay, great. So first of all, I'd like to thank Dan and Emily for organizing this very interesting and relevant webinar. My name is Karen Mazuma, and I'm a PhD student here at Columbia University, where I work at NASA GISS under the supervision of Susanna Bauer and Kostas Tigouridis. And I'm basically doing the fire modeling component for the NASA GISS Earth System Model. So today I'll present PIRE, which is an interactive fire model within the ESM, sorry. And, you know, the motivation for the work, as was previously stated by the speakers, is both on the climate aspect, but also to a certain aspect on the sort of weather and human impacts in the form of air pollution. So here in the background, you can see a satellite image from the infamous Thomas fires, and we can see how fire smoke really affects the radiative properties of what the satellite observes, and how this is, you know, it's also a very big issue for air pollution. So some more motivation. Fire activity is driven by both the environmental parameters, so you know, the weather, the temperature, relative humidity, precipitation, but it's also very much affected by human behavior. Humans are igniting fires, whether that's accidental or intentional, and that leads into fire effects. So fire are a source of air pollution. The smoke of the fire is a very important air pollutant. But also fires have a range of climate impacts, from biogeochemical cycles to radiative properties of aerosols, also black carbon deposition on ice caps. And lastly, this is something that we started to look at here at GISS, courtesy of Robert Field. Can fires affect weather? So here we have a clear sky AOD image from August 15, and we can see, you know, the very clear smoke plume over Canada. And what we're looking into now is whether fires can actually affect weather, and you know, how does the fire smoke affect surface temperature? So, you know, that's just more motivation for modeling fires. Simulating fires interactively is a tool to study biosphere forcing and feedback. And in the framework of an Earth system model, we can go and look at the past, the present, and the future. Now, going into the nitty-gritty details of PIRE. We first calculate our initial fire condition in the form of flammability. So flammability takes into account surface temperature, surface relative humidity, accumulated monthly precipitation, and the vegetation density in the form of leaf area index. Currently, we do not have dynamic vegetation, so you know, we assume that we assume present day LAI for past and future. A dynamic vegetation model is under development, and in the future we plan to integrate the fire model with our dynamic vegetation model. Anyway, so first we calculate flammability, and then from flammability we look at what the cloud to ground lightning is doing, and our cloud to ground lightning frequency is basically our natural ignition. So this is something that the GIS model interactively calculates. Then we use population density maps, where population density changes over time, increases over time. And we're using parameterization for anthropogenic ignition. Basically, we have sort of an empirical scaling factor that includes the magnitude and the spatial distribution of the fires. From ignition, we go into suppression, and we calculate suppression using the same population density maps, where we assume that that the fire suppression ranges according to the population density. So basically, 5% of the fires in unpopulated areas are suppressed, and 95% of the fires in densely populated areas are suppressed. So flammability, ignition, and suppression goes into our fire count calculation. We also have a scaling factor that is based on modest fire counts. And this work, the parameterization that I've presented so far was something that was initially established by Olga Piccioni and Drew Schindel that worked here at GIS. And I took this work, put it in the climate model, and made it interactive. And to do that, I also added a few additional components. So PIRE has a fire spread area where we take the surface relative humidity, the surface wind speed, and also the vegetation type in the grid box to calculate a fire spread area. This is based on CLM's parameterization. So basically, we assume a point ignition, and then the spread area is this ellipsoid, which is driven by the relative humidity, wind speed, and vegetation type. From fire counts and fire spread, we calculate the burned area, and then the burned area goes to suppress the flammability. So our burned area at a given moment is the newly burned area plus the previously burned area minus the area that we covered. Now, I hope you can see this animation where I calculated the offline burned area. So I'm using here the parameterization that I just presented with modest fire counts, modeled surface relative humidity and wind speed, as well as the vegetation type and vegetation recovery following the dynamic vegetation model that we have as part of the GIS ESM. So we can see in the left-hand side, we have the modeled burn area. In the right-hand side, we have the GFED4S burn area. And we're basically looping over the months of the year 2001. You can see that in terms of the spatial distribution, we get the modeled burned area matches the GFED burned area, but in terms of magnitude, we do underestimate. So that's something that we're trying to, work on improving. Now you can see the full scheme of the fire model, and the next step, or the step that I'm mostly interested in, is going from the fire into the fire pollution, going into the emissions. So from fire counts, we go into trace gas and aerosol emissions. The way we do that is that there is a one-time offline calculation for an emission per fire count factor. So basically, I'm using modest fire counts and a reference emission inventory. It can be GFED emissions or any other fire emission inventory to calculate an emission factor per fire count. And this is how it looks like. Basically, different surface types emit different amount of different species. So we can see in the different color bars the different species that are being emitted. And what really pops up here is the fact that fires mostly emit CO and organic carbon. Fires are a very big source of black carbon, but when you look at smoke, what's the color of smoke? It's much whiter than black. So for people thinking about atmospheric chemistry and what does fire do to the atmospheric composition, it emits a lot of organic carbons. So these are our emission factors. You can see that there's a large variability between the different vegetation types and the different species. So this is a one-time offline calculation, and then we take these numbers, we put it in the model, and every time where the model calculates a fire count, it uses these factors to give us an emission. Now, from emissions, we go into ambient concentrations, and these are set by the model of physics and chemistry, meaning the transport, deposition, and chemical interactions. Now I'm going to show you a few applications of the fire model. So first, study fire pollution and health impacts. So what we have here is the surface PM2.5 concentration, excluding dust and sea salt. The upper three panels are for the pre-industrial, for the year 1850. The middle panels are for present day, for 2005, and then the lower three panels are for 2100, following RCP 8.5. And we can see in the left panels the total surface PM2.5. In the middle, we have the all surface PM2.5 excluding fire. Basically, it's a simulation that we had turned off fire. And then when we look at the difference between the two, we calculate our fire pollution. This is sort of an indication of the global fire pollution. And we can see that regardless of time period, fire pollution is high, and it's especially high over the tropical continental regions. Another interesting thing that we see is that fire pollution, we calculate that fire pollution in the pre-industrial accounts for 41% of the total surface pollution. Then, at present day, we have a lot of industrial pollution. So fire pollution goes down to be only 22%, even though in terms of the average mean value, it's a similar value. But then when we go into the future, with RCP 8.5, goes the assumption that we have emission controls on aerosol pollution. So we see that in the future, fire pollution will play a bigger role, both in the average global mean and in the percent of the total. Now, a second application of the fire model is to look at its climate impact and radiative forcing. So what we have here is the shortwave radiative forcing of fire aerosols. So again, we're looking at the difference between two simulations. And in the left-hand side, you can see the seasonality of the fire aerosol shortwave forcing. And in the right-hand side, the spatial distribution. And we see that, overall fire aerosols have a cooling effect on the climate system. That's not surprising. I just mentioned a few slides ago that fires, they do emit a lot of black carbon, but most of their emissions are in the form of organic aerosols. So These organic aerosols are reflecting solar radiation, thus have a cooling effect on the climate system. But one might ask, what is the seasonality that, we observe? Why is there, what drives the seasonality? And so to a first degree, the seasonality follows the seasonality of biomass burning emissions. But what happens around January to April is an interesting point. So one needs to remember that this is an interactive Earth system model. So when we look at the shortwave forcing, there's no simple answer. There's a lot of interactions that go into play here. And so trying to figure out what is the warming signal, we looked at the dust emissions and the dust load. And we saw that the global warming signal that we see is driven by a decrease in dust emissions and dust load due to a decrease in wind. Now, two things could be here at play. First of all, we might have some fire climate feedback that is affecting the wind and thus affecting the dust. But we might also have some effects of natural variability. These are two different runs that we are comparing. So these are really preliminary results, and to pin down what exactly is happening, it definitely requires further investigation. But when we look at the annual climatological mean, we see that still fire aerosols have a cooling effect on the climate system. Again, these are the reflecting organic aerosols that are driving that cooling. When we go into the pre-industrial, we see a weaker forcing, but we also see less fire emissions. If we exclude mineral dust and sea salt, which are, interacting and basically exerting their forcing, if we exclude that, we see really a strong cooling signal from the organic aerosols. So just to conclude everything, we saw that fire pollution is substantial in the pre-industrial, present day, and future. We see that the strongest fire pollution is in the tropics, where we have the biggest fires. We also saw that overall fire aerosols cool the climate. That's due to organic aerosols. And to a first degree, this is controlled by biomass burning emissions, by the seasonality of the emissions, and also the magnitude of the emissions. But complex effects here are at play, and this, the model is still under development and testing. So there is further investigation to study these fire climate feedbacks as well as the natural variability. So with that, I'd be happy to take any questions.
That was great, Karen. We have time for probably a quick question if anyone has one for Karen. Yeah, Ben.
Hi, this is Ben in the room. Thanks so much for the presentation. Could you say something about the warming effects from CO2 from fires and how that might affect the net radiative forcing effect kind of over longer timescales?
Yes, that's actually a great point. And with the fire model and basically with the GIS model, we don't interactively simulate CO2. CO2 fields are read in, and so definitely, fires also emit a lot of CO2 and have a warming impact. But that's not something I look into. and I guess, you know, it's something that we do want to do in the future, and I think we'll get to coupling the CO2 with the fires when we also get to the dynamic vegetation model being fully interactive with the fires. So right now I'm showing the slide where you see all of the different species that the fires emit. And so my focus is on the aerosols, the organic and the black carbon, but also the precursors of the inorganic aerosols, SO2, NOx, and ammonia.
Great, thank you.
Karen, is Pyre going to be part of the default configuration of Model E?
Pyre is going to be an option, flavor of Model E. I think that the default configuration is using the CMIP6 fire emissions, which are based on GFED4S. But it's, you know, it's there as a turn on, turn off, and we like to use it to compare with the emission inventories.
Okay. Yeah, Francesca had shown that in the ECMWF work, some of this, you know, the aerosol feedbacks can help reduce known model biases. I mean, is there do you have a feeling, or is there a feeling in the lab that including Pyre can help to reduce some of these radiative anomalies in the or radiative biases in the model?
Yeah, that's a great point, and definitely something that we want to investigate. But I think at this step, it's you know, probably too early to say. There are so many different model biases, and so we would need to, you know, focus on very specific case studies to evaluate that.
Okay. Yeah. Well, that was great, Karen. Thank you so much for the presentation.
Thank you.
Okay, and our final speaker is Sam Raven. Sam, are you there? Hey, Sam, are you there?
I'm here. Sorry about that.
Okay, great. Yeah. No problem. So if you could click the Quick Start tab and then the Share Screen button, we'll be able to see your slides.
All right. How's that look?
Looks great. Yeah, whenever you're ready, go ahead.
Okay, thanks. Yeah, thanks, Dan, for putting this together. It's been some very interesting talks already. I am a postdoc at the Karlsruhe Institute of Technology in lovely Garmisch-Partenkirchen, Germany. I'm working with Ahmet Arnef in the Plant Atmosphere Interactions Group. For my PhD, I helped develop a fire model for the NOAA Geophysical Fluid Dynamics Laboratory land model LM3, which is also coupled into an Earth system model. So Karen, it was very interesting to see the developments that have been going on with Pyre. Just to make sure that everyone's on the same page, although Karen did a very good job of introducing global fire models, these are models designed to simulate fire occurrence at large spatial scales for decadal to century scale simulations or longer. So not the sort of seasonal scale predictions or analyses that Francesca and Etienne talked about. These models use environmental parameters, including weather, live vegetation, dead fuel, and human influences to predict burned area. And they're mostly incorporated into global vegetation models so that disturbance there is correctly simulated. They're not really designed to be applied for seasonal forecasting and are mostly applied at resolutions of a quarter degree at finest. Models typically fall into one of the two broad categories. There are the empirical global fire models, which essentially treat the problem as a regression equation, where burned area is being determined by the environment. And then there are process-based fire models, for example, what Karen just presented, that attempt to some extent, actually simulate fire ignition spread and extinction. This is very similar to what Karen already showed you. One of the assumptions in process-based fire models is that total burned area is the product of number of fires and fire size. And so essentially, once you have an ignition, you assume that it spreads like an ellipse, so that and that's how you calculate fire size. And we call these process-based models, but they are necessarily empirical at some root level. So here I just have some of the equations from the, in gray are the equations from the Lee et al. Model that Karen talked about. And in blue are the equations that I ended up using in my model. So for example, here, this is the net effective population density on fire. You can see that it's unimodal around 10 people. So anyway, this is just sort of an example of what we're talking about here. Over the years, a huge number of fire models have been developed, starting with the introduction of NC Fire by Lenahan and colleagues in 1998. After that, fire quickly became a common process to include in global vegetation models. And papers describing new fire models proliferated. Some of these models have actually already been iterated upon, in some cases several times. So that when I entered the field during my PhD, which was around 2011, I was working on LM3, and there wasn't really any way, as I looked through the literature, to assess what fire models performed well, or even which processes seemed the most important to include in my model. Yes, every model description paper did include some kind of testing against observations, but most such tests varied in their simulation details or their choice of observational data. What was needed was some kind of standardized comparison. And thus was born the Fire Model Intercomparison Project, which was established and continues to be led by my supervisor, Ahmet Arnett, as well as Stan Hansen, who at the time was a postdoc with Ahmet and is now working with Jim Randerson at UC Irvine. I think I noticed that Jim is going to be one of the key speakers at the next one of these webinars, which is a lucky thing for y'all. He's a great speaker and extremely smart. So I heard about FireMIP from a visiting researcher at my university and joined the project in time for this first workshop, which was in September 2014, and we kind of hashed out exactly what we would be doing in a general sense, as well as the beginnings of a protocol for the first set of simulations. And I'm no longer primarily working on fire, but the fact that I'm in Ahmet's lab has meant that I've sort of continued to hear about FireMIP developments, and I've been participating in the workshops. This paper by Stain et al. In 2016 sort of lays out the groundwork. It's a very good review for global fire modeling in general, and establishes the need for FireMIP. One of the goals of FireMIP, as I said, is to test the ability of models to reproduce current patterns and historical trends of fire occurrence and impact using a standardized methodology. We also aim to compare models' performance to identify which model structures seem particularly useful and where more development should be focused. And finally, as a byproduct, we will generate estimates with uncertainty of fire pattern trends in the deep past, by which I mean the last glacial maximum, the 20th century, and the 21st century. There are a few guiding principles of FireMIP, the first of which is, of course, to standardize the simulations as much as possible by using a common set of input data for climate, carbon dioxide, human population, and lightning. The observational data to which we compare the models should be as independent as possible from any modeling. So, for example, we may not want to use the Global Fire Emissions Database because while their burned area are derived from satellite observations, the emissions estimates rely on fuel loads from a vegetation model. This point is an important part of the methodology for model benchmarking described by Kelly et al., which seeks to translate model performance into standardized metrics that can be compared among models and also against null models. I'll talk a little bit more about that later. The results I'm presenting here are for the first phase of FireMIP, which focused on the past century or so. I won't get too much into the details, but following model spin-up, we began simulations in 1700 or around 1860 for a couple of the models, with time-evolving input data. I'll be showing you the time series of global annual burned area that the model simulated as well as maps of mean burned area over the period for which satellite records are available. We also performed in this phase some sensitivity runs where we either held fire constant or turned it off entirely, or where we held constant various drivers of fire, such as carbon dioxide, which controls fire via vegetation, or lightning, or human population density for ignition purposes. We hope that these can be used to shed light on what parts of the fire system drive the models and real-world fire regimes in different regions. However, analysis of these runs is still at a very early stage, so I won't be presenting any of those. This impossible to read table presents some various details of the models that participated in phase 1 from the paper I led last year describing the protocol. As part of that paper, I put together a huge set of tables describing every participating model in complete mathematical detail, something that I still can't believe was ever suggested and that I agreed to follow through with. So for example, this table describes the calculation of combustion for models that classify dead fuels by size. If you are interested in learning more about global fire models, this is a fantastic resource, if I do say so myself. And in fact, it might actually even be better than some of the original model description papers. For example, while putting these models together, these tables together, we discovered that the combustion of live fuels is specified differently in 2 places in the original Spitfire paper, which was Sonica 2010, and that the Spitfire-based models in FireMap do not actually all use the same version. So for these 100 and 1,000-hour fuels, which are large branches and trunks, these 3 models simulate that they do not get combusted at all, whereas Orchidee Spitfire looked at a different part of that paper, and they actually do have some combustion. So simply coming together for this already yielded interesting results before any runs were done. All right, so here I'll be showing you every model's time series of global burned area for the period 1901 to 2013. At the moment, you're just seeing the period for which burned area remote sensing products are available, which is since around the year 2000. The bracket on the right shows you the approximate range of various satellite-derived observations for that period. As you can see, most models get it pretty much correct for this period, with LPJS, GlobeFirm, and NC2, notable exceptions down at the very bottom. However, as we look back throughout the 20th century, you can see that the models diverge more and more as we get further away from the present day. In fact, they don't even agree on whether fire generally increased, decreased, or stayed the same. This is a sort of pattern you may be familiar with from other intercomparison exercises. The models are designed to perform well for the period for which we have observations, but underlying differences mean that they diverge further into the past or future. And I should say that diagnosing the different reasons for these opposite, in some cases, trends is one of the things that I'm most looking forward to hearing about from firemen. Here we're looking at maps of mean annual burned area as a fraction of land that burned, so percentage is down here in the legend, for the period with satellite observations. In the upper left for reference, I have the GFED-4S data, which if you're familiar with GFED, that's the burned area augmented by Jim Anderson's small fires algorithm. In general, most models simulate too much burned area in the tropics and not enough elsewhere. Fire in the Mediterranean basin, the western US, and South America is commonly overestimated, whereas too little burning is simulated in Africa and Australia. So the last thing I'll be showing you is a little bit complicated, and I'm unfortunately not as familiar with this as I am with the other analyses. But this is a formalized benchmarking approach we performed following the procedure described by Doug Kelly and colleagues in 2013. The idea is to quantify how well a model performs across a comprehensive range of aspects of the fire regime, as well as other important processes in vegetation models. Specially chosen metrics allow a standardized comparison between models and against null models. These null models are especially useful. For example, one is the mean model, which is what you would get if you just applied the mean observed value of burned area across the entire period, instead of trying to simulate it with the model you've been developing for years. The random model is a set of burned areas that's derived from bootstrapping the observational data. The general idea here is that if, according to these standardized metrics, your model performs worse than these null models, then you probably need to go back to the drawing board. So what I'll be showing you are the results for normalized mean error of burned area. So the lower the score, the better. Looking at burned area, you can see that most models, those in green, perform better than the null, so you can see the scores for the mean model is always going to be 1, and random is going to be slightly higher than that. So most models perform better than the mean for burned area, but they are worse at getting the interannual variability correct. So models in white are better than the mean model, but worse than random. Sorry, worse than the mean model, but better than random. And models in red are worse than both null models. I should say that the null model, performing better than the null model is a pretty low bar to set. And so generally, if you get a score of like 0.98, for example, that's still really not great. The scores for carbon emissions from fire generally reflect those of burned area, but they're usually a bit worse, even though simulated vegetation carbon is simulated pretty well. This is one of the really cool aspects of the Kelly et al. Approach to benchmarking, which is that you can apply it generally to any metric that you're interested in, as long as you have good observational data for it. Finally, the models do a poor job of simulating seasonality. So here, concentration refers to how much of a distinction there is between a fire season and a non-fire season, so how concentrated the fire occurrence is within a year. Phase refers to the timing of peak burning within a year. Sort of trying to figure out exactly why this happens and why we can get annual burned area correct, but the timing isn't so good, is something I'm pretty interested in. And that's something that people are going to be looking at in some spin-off papers. So for example, we've got papers focused on fire emissions or seasonality. We've got Stain compiling a paper that's generally about these results. There are papers delving into the sensitivity runs to explore the drivers of fire and to diagnose what model features seem especially important and effective. We've got papers in progress focusing on the results for particular regions, and papers focused on specific impacts of fire, such as on above ground carbon, biome distribution, fuel consumption, and water cycling. So these are not trivial undertakings, as you might guess, and the FireMyth is an unfunded project for most participants. If you're interested in helping with any of these analyses or participating generally in FireMyth, that would almost certainly be very welcomed. So please feel free to email me at the address on the next slide, and I'll put you in touch with the right people. Karen, it'd be great to have you on board as well. So with that, I'll thank Stain and Almut for organizing FireMyth, and of course all the collaborators and funding sources. And thank you for your attention.
Sam, that was great. Thank you so much for the presentation. Do we have any questions for Sam? On WebEx, send me a chat message if you have a question for Sam or any of the other speakers, actually, because we have a few extra minutes.
Yeah, hi Sam, this is nice talk. This is Anarita. I was just wondering, you commented at the beginning of your talk how the global fire models that are analyzing fire myths are different from those applied, for example, at ECMWF for seasonal prediction or subseasonal prediction of fire, and so specifically those process models. Can you comment, can you elaborate a little bit on that, on those differences?
Yeah, so the main difference comes from the fact that we're dealing with these very coarse resolutions, both temporally and spatially. When you're looking at a quarter-degree grid cell, you have much less information about the microclimate in which a fire is ignited and through which it spreads. So, if you're a fire manager and you're interested in, Northern California or something, you can, ideally you can get some data on how fuel is distributed at a finer scale. and you have a sense of the topography of the area, where the rivers are, whereas all of that is kind of eluded at the scales that we're talking about. So, for example, Gita Laslop has done some interesting work showing that wind in the products that we use and, of course, the models that we run is actually a really, really poor predictor of fire. It has basically nothing to do with how much burned area happens. And, of course, that's not true when you look at individual fires or you're looking at, like what Etienne was saying, you know, the Santa Ana ones weren't especially bad last year, but, of course, they contributed. They always contribute. But just generally, at the scales that we're talking about, wind doesn't turn out to play much of a factor. And so that's why we're hesitant to apply these to anything close to like seasonal forecasting, at least without significant extra development effort.
Thank you.
Great, thanks, Sam. Let's see, there's a question via WebEx that just came in. Are there any measurable impacts or findings in Europe or for the global climate from large-scale forest fires in China or Russia? And, you know, Sam, you can weigh in on this, or maybe Etienne, Francesca, or Karen also would like to weigh in.
Yeah, I don't think, I will cede the floor to others on this one.
Okay. Etienne or Francesca, do you have any, want to shed any light on that question?
Sorry, can you repeat the question?
Sure. So this person was asking whether there are any measurable impacts or findings in Europe or for the global climate from large-scale forest fires in China or Russia.
Well, I'm sorry, I mean, in ECWF, we don't really do that kind of simulation. So, I mean, this would be more, the problem that, I mean, the study I've shown are only limited to, I mean, actually, the data set that I've shown has just started to be explored. Therefore, we just looked at Indonesia, just because myself, I knew it was a big event. But we can have a look at these other cases as well. The person that is doing this work at ECWF is Angela Benedetti, and she's an expert of aerosol and aerosol assimilation. I will actually tell her if she can look also at the big fire in the Far East. I'm sorry, I don't have an answer for now, I'm sorry.
No, that's fine. Yeah, I mean, it sounds like it just hasn't been a focus.
I would like to quickly comment. So we haven't looked exactly on these fires, but I would expect to see an impact, especially black carbon deposition on the ice caps. And as I mentioned before, right now Robert Field is looking at some of the more broad-scale climate impact or weather impacts of the previous fire season in North America. So, no, we haven't looked at those specific Asian and Russian fires, but I would expect to see, you know, significant effects.
Thanks, Karen. Etienne, I saw you unmuted briefly. Did you want to weigh in on this?
Yeah, it's just a more general comment. I think it's mostly the tropics that that suffer from a lot of fire emissions, and in those areas where you would have a very much more important impact on the climate. I think Karen's results were showing that the major differences when you, of course, it's just simulations, no, but the big impact of fire emissions and black carbon are more in the tropics. Now in China, I would much more be concerned about the effect of background pollution than the actual fires themselves. There was a study just recently in some fires in Greenland, which I saw in the EGU meeting last week, and they basically said that yes, there was some kind of impact. There were deposits of black carbon on the ice sheet, but its impact really wasn't that big because you have not much vegetation to burn in those specific areas, which are grasslands and maybe a little bit of the peat. So very different from the kind of very more dramatic effect of wildfires in the tropics.
Okay, thanks. Yeah, I think between the three of you, that was a pretty great answer. So thank you for that. And actually, the question asker thanked you all as well. So thanks for that thorough answer. Sam, I was wondering on your slide where you showed the results from each of the individual models for burnt areas. Are there paleo estimates from before the satellite era where you can kind of bound or give a sense of, you know, which of these models is more in the ballpark of reality? You know, a decreasing trend, a flat trend, an increasing trend.
Yeah, there are. So there's this one data set, and I'm blanking on the guy's name, which Florent Murillo, I think, is how it's pronounced. I think it was him who put together a data set for the 20th century of global burned area trends. And he did so through kind of a combination of fire records for places where that exists. So like in the western U.S., that goes back to the mid-20th century, and combine that with some charcoal stuff. The problem with charcoal data is that the more I learn about it, at least for me, the more I learn about it, sort of the less I trust it, to be quite frank. And so, especially when you're talking about very fine scales like this of, you know, a century, it's hard to know how much to trust any trends that you get. And when you're talking about, you know, trends from like across the Pleistocene, then that would be a really good application of the charcoal data. But yeah, the 20th century is this kind of awkward in-between phase where there's not really any good observational data. Generally, I think that the idea is that as agriculture expanded, there's been less fire. So you might think that the models with a decreasing trend across the time period have it more correct, but that's sort of a kind of just so explanation, I guess.
No, that's great. The other thing I was wondering is, do you have a sense, I mean, these models each individually have very different interannual variabilities. Do you have a sense of what the actual interannual variability of burnt area is? Like, is it lower? Is it like the red line model, or is it, you know, much higher like the gold or green models?
Well, that's a good question. And I wish I had included the line for a couple of the satellite products. I'm pretty sure it's more like the purple model, or, you know, just generally most of the models, where you have periods with big peaks, a lot of the time corresponding to these big global cyclic patterns like El Nino. And then you also have troughs in the burned area patterns. So I think generally the amount of interannual variability is simulated well by the models, but just the exact timing of when it's a peak or when it's a trough, as we saw with the benchmarking results, the models aren't very good at that.
Great. Thanks a lot, Sam. That was a really interesting presentation. So we're a little bit over time now, so I think we'll just wrap things up quickly. I want to thank the 4 speakers today. I know it's getting into the early evening for some of you in Europe, and really appreciate you dialing in. And I thought the presentations were all really fascinating and built on each other nicely, which was great. It's a really interesting topic. I hope that, you know, the speakers and folks who are still on the line can log back in next Tuesday for the second part of this webinar. Next week, I have it up on the screen, we're going to hear from 4 speakers again. We're going to hear from Uma Bhatt, who's at the University of Alaska Fairbanks. She's doing some work with the North American Multi-Model Ensemble for seasonal prediction. We're going to hear from Ed Delgado, who's at the Bureau of Land Management. He works on some of the operational products that are issued for the United States and North America. Adam Kochanski, who's at the University of Utah, and he's going to talk about an effort with WRF, the regional model where they've been doing some work on data assimilation and also smoke and other emissions from fires. And then Sam alluded to Jim Randerson from University of California, Irvine. His group does a broad array of research activities on fire, and he's going to talk about some of those, including seasonal prediction, but also some of the dynamics and aerosol and other chemical products from fires. So hope that you'll come back. A recording of this webinar should be up on the CPO webinar site in the next couple days, and the slides as well. And again, thanks to everyone for attending. Thank you to the speakers. I thought it was a really great webinar, and we really appreciate you taking the time to put together these slides and present. So thanks, everyone. Hopefully, we'll talk to you again on Tuesday.
Thank you.
All right, thanks. It was fun.